In this chapter, we will discuss the structures of molecules and the interactions between them. A valence bond structure of a molecular identity is represented with a Lewis structure. A Lewis structure is a diagram that shows the atoms, bonds, and excess electrons in a molecular identity. Each atom and its position in the structure is shown using its chemical symbol. Lines are drawn between atoms that are bonded to one another, representing the shared electron pairs. Excess electrons such as lone pairs are represented as dots and are placed next to the atoms. Lewis structures are usually used for small molecular entities with a single center. For large molecules, particularly organic molecules, the structures may be written in more compact forms, such as the skeletal formulae. To show the construction of Lewis structures, formaldehyde is used as an example. First, count the total number of valence electrons. It is the sum of the numbers of valence electrons on each individual atom. Core electrons are not represented in Lewis structures. When counting the electrons of polyatomic ions, negative ions should have extra electrons placed in their Lewis structures, vice versa. In the case of formaldehyde, carbon has 4 valence electrons. Oxygen has 6 valence electrons. Each hydrogen has 1 valence electron. The molecule has no extra charge, so the total number of valence electrons is 4 plus 6 plus 1 plus 1 is equal to 12. Second, determine how atoms are arranged. There is a tendency that the least electronegative atom is at the center, called the central atom. It is surrounded by more electronegative atoms, called the ligands. There is one exception that hydrogen is always ligand, despite of its low electronegativity, because it can form only one bond with other atoms. In the case of formaldehyde, carbon is less electronegative than oxygen. So, carbon is the central atom. Oxygen and hydrogen are ligands. Third, one line, representing a single bond consisting of a pair of electrons, is drawn between each pair of connected atoms. The remaining valence electrons are temporarily distributed first to the ligands and then to the central atom and drawn as dots, until there are no more to be placed. According to the octet rule, a light main group atom except hydrogen can have 8 valence electrons. No electron should be distributed to hydrogen because it has got 2 shared electrons from the single bond. In the case of formaldehyde, 3 single bonds consisting of 6 electrons are drawn to represent carbon-oxygen and carbon-hydrogen single bonds. There are 12 minus 6 is equal to 6 remaining electrons. All of them are distributed to oxygen so that it has 8 valence electrons. Then, no more electrons can be placed. Finally, if the central atom has fewer than 7 valence electrons, 2 unshared electrons are deleted from a ligand and an additional line is drawn between them. This represents the conversion of an unshared pair of electrons into a shared pair, which adds 2 valence electrons to the central atom while leaving the ligand's valence electron count unchanged. This step is repeated until the central atom has 7 or 8 valence electrons. When the Lewis structure of an ion is written, the entire structure is placed in brackets, and the charge is written as a superscript on the upper right, outside the brackets. In the case of formaldehyde, carbon has 6 valence electrons so far. Thus, 2 unshared electrons are deleted from oxygen and an additional line is drawn between them. Now, oxygen has 8 valence electrons. Formaldehyde is a charge-neutral molecule, so no bracket is needed. A formal charge is the hypothetical charge assigned to an atom in a molecular entity, assuming that electrons in all chemical bonds are shared equally between atoms, regardless of relative electronegativity. In simple terms, formal charge is the difference between the number of valence electrons of an atom in a neutral free state and the number assigned to that atom in a Lewis structure. The formal charge of any atom in a molecule can be calculated by the following equation, where V is the number of valence electrons of the neutral atom in isolation. N is the number of non-bonding valence electrons assigned to this atom in the Lewis structure. B is the total number of electrons shared in bonds with other atoms in the Lewis structure. For example, the neutral hydrogen atom in isolation has 1 valence electron. In the Lewis structure of formaldehyde, hydrogen has no non-bonding electron and 2 shared electrons. So, the formal charge of hydrogen is 0. The neutral carbon atom in isolation has 4 valence electrons. In the Lewis structure of formaldehyde, carbon has no non-bonding electron and 8 shared electrons. So, the formal charge of carbon is 0. The neutral oxygen atom in isolation has 6 valence electrons. In the Lewis structure of formaldehyde, oxygen has 4 non-bonding electrons and 4 shared electrons. So, the formal charge of oxygen is 0. Nitrate ion is used as another example. First, nitrogen has 5 valence electrons. Each oxygen has 6 valence electrons. The ion has charge of -1, so the total number of valence electrons is 5 plus 6 times 3 plus 1 is equal to 24. Second, nitrogen is less electronegative than oxygen. So, nitrogen is the central atom. Oxygen are ligands. Third, there are 24 minus 2 times 3 is equal to 18 remaining electrons. All of them are distributed to oxygen, so each of them has 8 valence electrons. Then, no more electrons can be placed. Finally, nitrogen has 6 valence electrons so far. Thus, 2 unshared electrons are deleted from oxygen and an additional line is drawn between them. Now, nitrogen has 8 valence electrons. Nitrate ion has a charge of -1, so the entire structure is placed in brackets, and a minus sign is written as a superscript on the upper right, outside the brackets. In some cases, more than one Lewis structure could be drawn for a particular molecular entity. When this situation occurs, each Lewis structure is said to be a resonance contributor, and the molecular entity exists as a resonance hybrid. The nitrate ion, for instance, must form a double bond between nitrogen atom and one of the oxygen atoms to satisfy the octet rule for nitrogen. However, because the oxygen atoms are equivalent, it does not matter which of the oxygen atoms forms the double bond. In this case, there are 3 contributors. Expressing resonance when drawing Lewis structures may be done by drawing each of the contributor and placing double-headed arrows between them. Among the contributors, the best one is chosen such that the formal charge on each of the atoms is as close to 0 as possible. For example, 2 contributors of azide ion can be drawn. In the first contributor, 3 nitrogen atoms have formal charges of 0, 1, and -2, respectively. In the second contributor, 3 nitrogen atoms have formal charges of -1, 1, and -1, respectively. So, the second contributor is better because the highest absolute value of formal charge is closer to 0. It is called a major contributor, while the first contributor is a minor contributor. In organic chemistry convention, formal charges are an essential feature of a correctly rendered skeletal formula, and a structure omitting non-zero formal charges is considered incomplete. Formal charges are drawn near the atom bearing the charge. They may or may not be enclosed in a circle for clarity. Meanwhile, the brackets and overall charge are omitted. When non-zero formal charges are necessary, contributors that have negative charges on the more electronegative elements and positive charges on the less electronegative elements are favored. For example, 2 contributors of nitrous oxide can be drawn. In the first contributor, the oxygen atom has formal charge of -1. The nitrogen atoms have formal charges of 0 and 1. In the second contributor, the oxygen atom has formal charge of 0. The nitrogen atoms have formal charges of -1 and 1. So, the first contributor is better because it has the negative formal charge on more electronegative oxygen. It is the major contributor, while the other is a minor contributor. For light elements, the octet rule overrides the formal charge rule. For example, 2 contributors of carbon monoxide are shown. In the first contributor, both atoms have octets, but the more electronegative oxygen has positive formal charge while the less electronegative carbon has negative formal charge. In the second contributor, both atoms have 0 formal charge, but only oxygen has octet. Experimental result shows that carbon monoxide has a stronger bond than carbon-oxygen double bond, e.g., in carbon dioxide. Meanwhile, oxygen has positive charge and carbon has negative charge. So, the first contributor with the octet on carbon but non-zero formal charges is the major contributor. When resonance occurs, experimental properties of the molecular entity are inconsistent with any contributor. The resonance hybrid represents the actual molecular entity as the average of the contributors, with bond lengths and partial charges taking on intermediate formal values in the contributors. For instance, in nitrite anion, each contributor has two different nitrogen-oxygen bonds. However, its measured structure has two equal nitrogen-oxygen bonds, intermediate in length between a typical nitrogen-oxygen single bond, e.g., in hydroxylamine, and nitrogen-oxygen double bond, e.g., in nitronium ion. This is consistent with a description as a resonance hybrid of the two contributors. According to the contributors, each nitrogen-oxygen bond is an average of a formal single and formal double bond, leading to a true bond order of 1.5. Partial bonds are usually pictured as dash lines. By the virtue of this averaging, the Lewis description of the bonding in nitrite ion is reconciled with the experimental fact that it has equivalent nitrogen-oxygen bonds. Meanwhile, according to the contributors, the formal charge of nitrogen is an average of 0 and 0, leading to a formal charge of 0. The formal charge of each oxygen is an average of -1 and 0, leading to a partial formal charge of -0.5. Resonance is caused by the delocalization of electrons. Electron delocalization stabilizes a molecular entity because the electrons are more evenly spread out over the structure, decreasing electron-electron repulsion. So, any species represented by a resonance hybrid is more stable than any of the contributors. For example, in nitrite ion, the molecular orbital model gives 3 pi molecular orbitals, which are combinations of the 2 pz atomic orbitals on the nitrogen and oxygen atoms. Thus, each pi molecular orbital is delocalized over the whole ion, and any electron occupying a molecular orbital will be delocalized over the whole ion. In benzene, the two cyclohexatrine kekale structures are taken together as contributors to represent the hybrid structure. In the hybrid structure, the dashed hexagon representing delocalized pi bonds replaces 3 localized pi bonds. The molecular orbital model gives 6 pi molecular orbitals, which are combinations of the 2 pz atomic orbitals on each of the 6 carbon atoms. Thus, each pi molecular orbital is delocalized over the whole benzene molecule, and any electron occupying a molecular orbital will be delocalized over the whole molecule. This molecular orbital interpretation has inspired the picture of the benzene ring as a hexagon with a circle inside. A molecule connected with delocalized pi electrons is called a conjugated system. It is conventionally represented as having alternating single and multiple bonds. Linear polyenes and polyaromatic compounds are typical conjugated systems. They have backbones of contiguous sp2 hybridized carbon centers. All the pz orbitals, which are orthogonal to the sigma bonds, combine with each other to form molecule-wide delocalized orbitals. The electrons in delocalized orbitals have high mobility, so conjugated system may have metallic conductivity or can be semiconductor. So, conjugated polymers are conductive polymers.